All right, so welcome to another one of the master classes, and today we're going through the Cambridge International Examinations AS level paper, paper 21. It's a structured, a set of structured questions, and this is from 2 years ago, winter 2015. So, let's get myself going. Okay, good. All right, so the paper starts off with some questions about aluminium, and as in some of the other master classes, we'll work through the answers and explain them in a little bit more depth than the mark scheme does, but we'll also pick up on the kind of comments that the examiner feeds back about the way the students have handled these questions after the exam has been completed and reviewed in 2015. So we'll be putting in examiner's comments, and one of the ones that the examiners made at this point was that a lot of students said, well, they could describe the structure of solid aluminium, and they could say there were delocalized electrons. That's an important part of the metallic structure of aluminium. But the students were less good about saying that these delocalized electrons were within a lattice of cations, meaning that that the structure is down here. You've got a lattice, that means a regular repeating structure of cations, and in between the cations are delocalized electrons. So in the case of aluminium, those cations, of course, are aluminium 3+. And the things that the examiner was looking for was, well, first of all, you had to say that there were delocalized electrons. That was an easy mark. But then the mark that a lot of students didn't get was to say that there was a lattice or a regular or repeating arrangement of cations. So that was the second point there that was much harder for students to get. Those are the 2 points you get for your 2 marks. Okay, so properties of aluminium that make it suitable for cables. Obviously, it's got to be a conductor. And the examiner said, well, a lot of students wrote conductor, but they weren't specific enough. Was it a good conductor of heat or a good conductor of electricity? Is it properties of thermal conduction or electrical conduction? So really, to get the full mark there, you needed to say that aluminium was a good conductor of electricity or a good electrical conductor. You're distinguishing it from being a good thermal conductor, and that was the discrimination that the examiner was looking for. And then you know that aluminium has a low density, so if you're stringing aluminium cables up on pylons, they don't need to be heavy, so the mass per volume is low for aluminium. It has a low density, and then these cables are going to be outside all the time, and so you need to say that aluminium is corrosion resistant. Actually, you only need to do 2 of these, don't you? You've got 2 marks. So you could choose any 2 of those, but just make sure that when you're saying it's a conductor, you're saying clearly that's a good conductor of electricity. It's not a thermal conductor. Okay, so these aluminium cables, they're held to the pylons by these ceramic supports. And so the examiner is looking here for the structure of a ceramic material. There's only 1 mark, but it is it's a difficult answer to be correct about, because ceramics are quite difficult to define. So with the ceramics, the official UPAC, the International Union of Pure and Applied Chemistry, their definition of a ceramic is a material that has been sintered. And what they mean by that is that you take some kind of substance that has crystals, a bit like this, small crystals, and you heat it, but you don't melt it completely. It doesn't become a liquid. You just sinter it. And that means that the edge of these crystals start to melt, but not the interior of the crystals, just the edge. And as the edges melt, then they all kind of glue into each other with the crystal material that's been molten just on the edges. So can you see you've got these sintered crystals that are now embedded in this kind of network here, and that network is all covalently bonded. So it's a giant covalent structure. Now you can see here, because some of these solid crystals didn't completely melt, they just kind of melted at the edges and fused into one another, then the composition isn't consistent. Here you've got some crystal, over here you've got mostly molten material that's solidified again. And so it's not a consistent composition all the way through. And so the way to describe that is to say it is heterogeneous. Something that had a consistent, uniform composition all the way through would be homogeneous. And so these are the kind of words, you know, you've only got one mark here, but we're just going through them. These are the kind of language that you're using to describe a ceramic material. So the composition is heterogeneous, and the ceramic is derived from having been sintered, and it's a network of giant covalent. It's a network of a giant covalent structure with some crystals fused within it. So actually, if you look in the mark scheme, they were only looking for giant covalent structure, and that would have given you the mark. But let's say you're in a different exam and there's more marks required, you could say something like a heterogeneous solid of sintered crystals fused together. That would be you know, a much richer description of a ceramic material. But for the point of going through the paper here, your one mark was for saying that it was a giant covalent structure. Now, if you look at that, this giant covalent structure with these crystals that have been sintered here, well, there's no delocalized electrons, and there's no ions in there. So even if this was a liquid, there's no ions that are free to move. So for both those reasons, the ceramic material is an insulator. And we need to distinguish again between a thermal insulator and an electrical insulator. So you need to say there that it's an electrical insulator, and that's why it's good for hanging these power cables from the pylons. It's an electrical insulator. Well, there's no delocalized electrons, so no current can flow in the solid state. And just for information, if we melted the ceramic material, well, there's no ions there either, so it can't conduct electricity in the molten state either. It's a good electrical insulator. All right, now, coming along here, we're looking at a compound of aluminium and chlorine, and it's changing from a solid to a gas, and the technical word for that is sublimation. It sublimes, and this is at a relatively low temperature. So when something has a low sublimation point, or a low boiling point, or a low melting point, that should be triggering in your mind that this is a simple, pen's not working, simple molecular substance. You have to excuse my writing with this pen. A simple molecular substance, meaning you've got small molecules, and within the molecule are covalent bonds, and between the molecules are intermolecular forces. So you've got to describe the structure and bonding in this compound here. So you're going to say within the molecule there are covalent bonds, and between molecules there are weak intermolecular forces. Now you should know there's three different types of these weak intermolecular forces. There's London forces, they're sometimes called dispersion forces. There's dipole-dipole attraction, and there's hydrogen bonding. Now, of course, when you've got aluminium and chlorine as the only elements in this covalently bonded molecule, well, there's no hydrogen bonding possible. So the intermolecular forces are going to be either dispersion forces, they're sometimes called London forces, or dipole attraction. Two types of forces, two types of intermolecular forces. And because these are weak forces, weak intermolecular forces between the molecules, then you need a relatively, excuse my writing, relatively small amount of energy to overcome the weak intermolecular forces. So, I think you've got to get all of that in for your 2 marks, that within the molecule there are covalent bonds, between the molecules there's weak intermolecular forces. They're either dispersion forces or dipole-dipole forces. It could be both, actually. And then, because we've got a low sublimation point, those intermolecular forces have a relatively small amount of energy is needed to overcome those forces. Okay, in determining empirical formula, well, it's told you up here, hasn't it, that in this molecule, can't get the pen to write, there's, hang on, you have to excuse me while I just do all of that. Okay, all right. So within this molecule, there is chlorine and there is aluminium. And it told us that there was, what was it? 79.7% chlorine. Now the rest of it is aluminium. You just do a quick calculation and that gives you 20.3% aluminium. That's the percentage. Then you would say, well, the mass in 100 grams would be, well, this is easy stuff, isn't it? 79.7 grams of chlorine and 20.3 grams of aluminium. That's just taking the percentage and saying, well, in a mass of 100 grams, you've got that many grams of chlorine and that many grams of aluminium. You can then look up in the periodic table the molar mass of chlorine and aluminium. And for chlorine, you can look that up. That is 35.5 grams per mole. And for aluminium, that's 27.0 grams per mole. And if you know the mass and you know the molar mass, then you can calculate the amount. Symbol for that is N units moles. That's the number of moles. And you should know that the number of moles is the mass, we had that in the column there, divided by the molar mass in grams per mole, which we've got there. And you can work out the number of moles, the amount. If you do that calculation, you get 2.245 moles for chlorine and 0.752 moles for aluminium. And then you need to work out the ratio of those, which means dividing through by the smallest number. So that divided by itself is 1, and that divided by the smallest number becomes 2.99. But the empirical formula is the smallest number where you've got whole numbers. So you've got to have the smallest whole number ratio here. And so you can see that you've got 3 there and 1 there as your smallest whole number ratio. Okay, so you've got a ratio of 1 aluminium to 3 chlorines. The empirical formula is AlCl3. Okay, now the examiner's comments were, well, it's not good enough just to write down the answer because you might know it. You've got to show your working, so don't forget your working. The examiner said that sometimes students, instead of having chlorine atoms, for some reason we're thinking of chlorine molecules, you're just working with chlorine atoms here, and some students at the end of the calculation got mixed up about which coefficient went with which atom. So 1 is implicit there, isn't it? Al1, and 3 for chlorine, Cl3. So don't get those mixed up. Good, so we've got the empirical formula, and now we're going to work down here to work out the molecular formula a bit later on. But the first thing that they want to need to calculate is the relative molecular mass of this chloride. And they're giving you a temperature here, they're giving you a pressure, they're giving you a mass, they're giving you a volume. And you could spot, couldn't you, that probably you're going to be using the ideal gas equation. So PV equals NRT. Well, we've got pressure, it's over there. You've got volume, it's over there. You've got T, the temperature. R, the gas constant, you can just look that up in the data book. And that should allow us to calculate N, the amount, the number of moles. And then if we've got the number of moles and we've got a mass, well, we can relate the number of moles, the mass, and the molar mass all together by that equation. And the relative molecular mass here is the same numerical value as the molar mass down here, which has units of grams per mole. But this, because this is a relative value, it just doesn't have any units. It's dimensionless or unitless. Okay, so it looks pretty easy stuff. It looks like we're just substituting values in. But where the question is going to catch you out is that you've got to make sure that the values that you put in here are dimensionally correct, meaning that they have the right units. Because some of the units they've given you up here aren't ready, as they stand, to be plugged into this equation here. So the temperature, well, it's given you in degrees Celsius there. The temperature in the universal gas equation, or the gas equation here, the temperature has to be in Kelvin. So to convert a value of degrees Celsius into a temperature in Kelvin, you've got to add 273, haven't you? So the temperature actually is 473 Kelvin. Okay? Now you've got the pressure there, and that's in kilopascals. A pascal is actually a pascal is newtons per meter squared. So a kilopascal is 1,000 of those. So actually you want to be plugging in here not 100 kilopascals, but 100,000 pascals, or 100,000 newtons per meter squared. So that's the temperature. The pressure is 100,000. Okay, so we've had to do a little bit of work on the pressure there. And then the volume over here, because it's being plugged into this equation here, the volume should be in units of meters cubed. So you've got to convert from centimeters cubed to meters cubed. Well, you know that 1 centimeter, that's the same as 0.01 meters, yes? Because there's 100 centimeters in a meter. So 1 centimeter cubed, well, you've got to cube everything on this side. So that's going to be, that's 10 to the minus 2 meters, isn't it? So if we cube that, that's 1 times 10 to the minus 6 meters cubed. All right, so this is going to be not 200 centimeters cubed, but 200 times 10 to the minus 6 meters cubed. All right. Now, if we plug all those in, we need to rearrange. We're trying to get N, the amount, the number of moles, to be the subject of the equation. So that rearranging that gives us PV over RT. So P, well, that's now 1 times 10 to the 5, isn't it? And V is times 200 times 10 to the minus 6, because we calculated that earlier on, converting centimeters cubed to meters cubed. The value of R, we can look that up in the data book. That's 8.31 joules per Kelvin per mole. And then the temperature, well, we calculated that in Kelvin, didn't we? Because the gas constant here is 8.31 joules per Kelvin per mole. And if you multiply all those through together, you end up with 5.09 times 10 to the minus 3 moles, because you're working out an amount here, the number of moles. Very good. So we've got we've successfully got through using the ideal gas equation. We just had to make sure that we changed these various quantities into their correct units before we plug them in. We've got the amount, the number of moles, and you can see here that if we know a mass, there it is, and we know the amount, then we should be able to calculate the molar mass. So just rearranging that, the molar mass is the mass divided by the amount, the number of moles. So we've got to take that value for the mass and divide it by that value for the amount, the number of moles. And if you do that, you end up with a value for the molar mass equal to 267.12. Let's just make my 2 a bit clearer there. And the units of the molar mass are grams per mole. Now, to go from a molar mass to a relative molecular mass, it's the same numerical figure, but without the units, because this is a relative molecular mass. It's units, it's a relative number. And just checking back to the question, you've got to go to 3 significant figures. Well, if you put this to 3 significant figures, it's 2, 6, 7, and the last digit doesn't change because the following digit there that we're losing when we're going to 3 significant figures is only 0.1. It's not 0.5 or above. We're not rounding the 7 up to 8. So we've got to 3 significant figures, 2, 6, 7, and you just put in there, so it's absolutely clear, 3 significant figures. Very good. Okay, so we calculated there, didn't we, the relative molecular mass, and up here we've got the empirical formula, and it's asking us down here for the molecular formula. And to get the molecular formula, you've got to take the empirical formula, mass, its relative mass. Sorry, I got this wrong way around. You've got to take, that's my empirical formula mass, and you've got to take the relative molecular mass, excuse my writing, you've got to take the relative molecular mass that you determined over here and divide it by the empirical formula mass. Well, what's the empirical formula mass? Well, it's the relative mass of the empirical formula. Okay, so that means, look it up on the data book, the relative atomic mass for aluminium is 27. The relative atomic mass for chlorine is 35.5, but we've got to have 3 of those. 3 times 35.5 is 106.5. Added all together gives us an empirical formula mass of 133.5. So we're coming down here. Our relative molecular mass was 2, 6, 7, to 3 significant figures, and the empirical formula mass that we just calculated was 133.5. So, oops, 133.5. And if you do that division, you end up with an answer of 2. Well, what does that mean? That means that actually the formula of this compound is not AlCl3, but 2 times that, okay? Because the relative molecular mass is much higher, or 2 times higher, than the empirical formula mass by a factor of 2. And so we deduce that the molecular formula is not AlCl3, but 2 times that, Al2Cl6. Okay? Good. There's a question here about the enthalpy change of formation. You can look that up in your definitions. But the main thing about the enthalpy change of formation is that you are forming 1 mole of a compound. And the reactants and the products have to be in their standard states. Now, it's looking here for an enthalpy change, and we have to give an equation that represents 1 mole of this being formed from its elements in their standard states. So we've got to get to 1 mole of sulfur trioxide. Well, to get there, we've got the elements in their standard states. Standard state is oxygen gas. Standard state is some solid sulfur. Let's put in the state symbols there. But our target here from the definition is that we have to make 1 mole of the compound. So we can't change any of the stoichiometric coefficients here. Let's just see how this works then. So you've got 1 sulfur atom, 1 sulfur atom, the equation's balanced so far. You've got 3 oxygen atoms. Well, how are we going to get 3 oxygen atoms? Well, you're going to have to go to 1.5 of these oxygen molecules, because we, according to this definition that you had up here, we must only make 1 mole of the compound. So we've got sulfur, 1.5 of the oxygen molecules gives us 1 molecule, or 1 mole of the sulfur trioxide. Now we know the standard states were sulfur solid, oxygen's a gas, and we've got a clue here, haven't we, that we're trying to make this liquid. It's a liquid sulfur trioxide, so we put L in there for liquid. It's very important that you include the standard states, and the examiner said that, well, if you didn't put if you didn't put the state symbols in, the examiner is saying don't put the state symbols in, you don't get the mark. Next question about the Haber process. Got a pretty big clue here that we've got to go and look something up in the data booklet. And formally here, the enthalpy change is the sum, with all their stoichiometric coefficients, of the bond energies in the reactant. Take away, this is the sigma symbol, meaning the sum. N means we've got all multiplied up by the right stoichiometric coefficient. The sum multiplied up by the stoichiometric coefficient for the bond energies in the product. Yeah, that gives us the enthalpy change for the reaction. So we've got a nitrogen molecule, triple bonded, and we've got a hydrogen molecule, and there's 3 of those, and they're reacting to make 2 ammonia molecules. So you can see there we've got 1, 2, 3 nitrogen hydrogen bonds for each ammonia molecule. We've got 2 molecules, so altogether we've got 6 nitrogen hydrogen bonds. So we've got 6 nitrogen hydrogen bonds, and all we've got to do is we've got to add up the enthalpy that we'd need to break the bonds in the reactants, and the energy that will be given out actually when the bonds form in the product. So if you look that up in the data book, you've got a value for breaking that bond there of 944 kilojoules per mole. For each hydrogen bond, 436, but we've got 3 of those, haven't we? And for this nitrogen-hydrogen bond, you've got 390 kilojoules per mole, and you've got to multiply that up by 6, because we're forming 2 molecules of ammonia, each of which has got 3 nitrogen-hydrogen bonds. And so you add those all together, you've got 2,252 if you do the calculation, you've got 2,340 if you do the calculation here, and you're doing that sum, you see the sigma there, minus that sum, that was the sigma there. And 252 take away 2,252 take away 2,340 gives you 88 kilojoules per mole, and because you've taken a larger number away from a smaller number, that's a negative value. And so, you know, the examiner is looking for 3 marks here. You're going to get 1 mark for working everything out, you're going to get 1 mark for the answer, and you're going to get 1 mark for the negative sign because you took a larger number away from a smaller number. It's a negative enthalpy change. That's another way of saying it's exothermic, isn't it? Good. Let's scroll up here. Okay, good. This is just some recall. You have to know the essential operating conditions for the Haber process. Probably you studied that at GCSE. You've studied it again at A-level. You should know this. Just look that up. You need an iron catalyst. You need 200 atmospheres. That's quite a high pressure. And you need a moderate temperature between 4 and 500 degrees Celsius. You get 3 marks there for the pressure, the temperature, and the catalyst. And you've got to explain, well, why you made the particular values of temperature and pressure. And when we ran through that just now, I said that was quite a high pressure, about 200 atmospheres, and a moderate temperature, about 450 degrees Celsius. And you're going to say something relating to the rate, the position, I'm using shorthand here, of equilibrium, and you're going to say something about the yield. This is an industrial process. We actually are concerned about getting as much ammonia as we can. And we set up here that the pressure was quite high. But if the pressure goes up, well, you know, don't you, that if you increase the pressure, then there's going to be more chance of a collision between particles. So more chance of a collision because the pressure's gone up, then the rate's going to go up. That's good. That's what we want. We want the reaction to happen at a good rate. And if you increase the pressure, then according to Le Chatelier's principle, the system at equilibrium will move in a way to oppose the change that we're making of it. So if we put a large pressure on this, this equilibrium is going to move to the right to reduce the number of gas molecules present. That's effectively trying to reduce the pressure. So the equilibrium will shift to the right, and so the yield will increase because there's going to be more product forming. Now, if the temperature goes up, well, you know from your studies that if you increase the temperature, the rate is going to increase. You're going to have more collisions and a greater proportion of successful collisions. But remember, in the calculation that you did, this was exothermic, wasn't it? You had a negative value for your enthalpy change. It's exothermic. This is delta H is negative. And if we increase the temperature of a reaction at equilibrium that is exothermic, then that favors reactants, not products. And so the equilibrium is shifting to the left, and so the yield would go down, wouldn't it? And so the temperature doesn't really want to be too high, because if we have it too high, then the equilibrium shifts to the left and the yield goes down. But there's no point waiting around for the optimum yield in this industrial process. We can't wait forever. So we've got to have some compromise here between a temperature that's high enough to give us a good rate, but not too high to start impacting the yield by shifting the position of equilibrium towards the reactants, towards the left. And so the examiner is looking for an argument that talks about a compromised temperature that gives us a good rate but doesn't impact the yield too much, and a high pressure that gives us a good rate and, according to Le Chatelier, gives us a good yield. So that's the kind of argument. I mean, I haven't written it out in words there. You'd have to do it in words. You'd have to be using vocabulary that's talking about making sure you've got a good rate, where the position of equilibrium is shifted when you have a high pressure and a moderate temperature, and some discussion about the yield, because it's an industrial process. We're actually concerned about getting a decent yield of ammonia. Okay, continuing on, talking about ammonia being used in this fertilizer here, ammonium diammonium hydrogen phosphate. Very easy. You've just got to write an equation here where you're writing the reaction between ammonia, aren't you, and phosphoric acid. I think you just look this up in the mark scheme rather than me writing it out here. H3PO4. That's going to I mean, it's pretty simple stuff. You're getting two molecules of ammonia reacting with one molecule of the phosphoric acid to give you this diammonium salt. It's diammonium, two, yeah? Two di. Okay, so we've got to explain that reaction in terms of Bronsted-Lowry theory. Well, if you look at this molecule here, it's actually ionic because you've got two ammonium ions, haven't you? NH4 plus, and you've got HPO4 minus. All right. So what happened here was that two of the hydrogens here, two of the protons, were given from the phosphoric acid and were accepted by the lone pair of electrons on the ammonia molecule. So this acid was giving away protons, or it was donating protons, you would say. And the ammonia molecule was accepting the protons. And so we've got 2 marks here. So you'd say, in terms of Bronsted and Lowry theory, so phosphoric acid was proton donor. Proton is just the hydrogen ion. And the ammonia, you can see what I mean. Well, I'm talking, the writing's not very good. The ammonia was the proton acceptor. And there's 2 marks there, so the examiner is looking for you to talk both about proton donor, the acid, and the proton acceptor. The ammonia is a base, isn't it? A Bronsted and Lowry base. Good. Are we done? Yep, good. Okay, quite a wordy answer coming up here, talking about what happens to nitrate fertilizers once they get washed off fields into rivers. There's 3 marks here. We've got to pack in quite a lot of vocabulary. Sometimes, the examiner didn't say it on this occasion, but it's quite good sometimes to give bullet points. You know, I think that sort of organizes your thoughts a bit here. So you could say that nitrate fertilizers, excuse my writing, are washed from the land into rivers by rainfall. That's the first point. The second point is that when these fertilizers end up in the water, then that stimulates the growth of water-based plants. And so you get overgrowing. These plants have never had it so good. They're really growing because of all the fertilizers that have been added. So you get overgrowth of the aquatic plants, and the technical name for that, you know, is eutrophication. Okay, so good vocabulary. Overgrowth or eutrophication of aquatic plants. And when those plants die, then the bacteria that assist in the decay of those dead plants consume oxygen from the water. So bacteria involved in the decay processes of the dead plants, all the overgrowth, consume oxygen that's dissolved in the water. You have to excuse my writing, I'm talking so you know what I mean. And because all these bacteria that are involved in the decay of these dead plants are consuming oxygen, that means there's a lot less dissolved oxygen in the water. And the technical word for that is hypoxic or hypoxia. So hypoxic conditions, insufficient dissolved oxygen, insufficient dissolved oxygen. So other aquatic animals, such as fish, that need a certain amount of dissolved oxygen in the water, aquatic organisms die. They don't have enough oxygen left to breathe through their gills in the case of fish. So yeah, I mean, that was one way to organize your thoughts and to make sure you're targeting 3 marks, because you could just go on and on about overgrowth or something like that. You've got to discipline yourself to have at least 3 points. I went for 4, didn't I? The bullet points just help you organize the thoughts and make sure that you're claiming the 3 marks that are available to be got at that point. Okay, next one. It's talking about the release of oxides of nitrogen into the atmosphere. All right, and what you're looking at here is that the oxides of nitrogen, when they go into the atmosphere, well, there's plenty of water in the atmosphere, in the clouds, that's going to make a mixture of 2 acids. You've got the nitrous acid and you've got the nitric acid. There's the 2 acids that are formed when the oxide of nitrogen, nitrogen dioxide, goes into the atmosphere. Just balance that up to give the correct stoichiometry for the equation. So we're making 2 acids. So the problem with that, of course, is acid rain, and that acid rain can destroy destroy plants, particularly, I mean, the famous cases for acid rain is the destruction of European forests. It can destroy plants, and you could say weather buildings. Excuse my writing. So only 2 marks available there. You had to get an equation showing the nitrous and the nitric acid, the acids that are forming from the nitrogen dioxide in the atmosphere. And then the problem is you've then got water with these acids dissolved in it. It's going to fall as acid rain. That's going to damage the plants and the forest, damage buildings as well. Good. All right, next one then. Heptane. Now, you've got to explain here a couple of words about isomerism, structural isomers, and this is optical isomerism, isn't it? When you've got chiral centers. So the examiner is looking for really tight definitions here. You're going to say very clearly here that a structural isomer, structural isomers are different molecules with the same molecular formula, but different structural formulas. So you're going to write that out. You can look that up. I'm not going to write it in. You're looking for different molecules with the same molecular formula, but different structural formulae. And for chiral, these optical isomers, you're looking for a carbon group with 4 different groups of atoms bonded to it. So that's 1 carbon with 4 different groups or atoms bonded to it. So you've defined there the structural isomers and the chiral center that you get in optical isomers. Good. Seem to be getting some extra menus here. Let's get rid of those. And there we go. Okay. Okay, so now we've got to give some structural isomers, because we're combining both of those things we just defined, the structural isomers that have chiral centers. And the way you can do this is it's really easiest to sort of draw out the displayed structure. So for the first one, I'm going to do this. And there's a methyl group just coming off the chain there. And you've got, continuing the chain here. So that's one of the isomers of C7H16. You've got 1, 2, 3, 4, 5, 6, 7 carbons, 16 hydrogens. And you've got to give the name of that. All right. So when you're naming these organic compounds, you've got to think of the stem. You've got to think of the suffix, and you've got to think of the prefix. And all those different parts taken together are going to give you the name of the organic compound. Well, the stem, start there. The stem is based on the longest carbon chain. Well, that's there, isn't it? So 1, 2, 3, 4, 5, 6. That's longer than counting that way. 1, 2, 3, 4, 5. So the stem is 6. When you have 6, then you use the word hex. Okay, hex. It's an alkane, isn't it? So the suffix is going to be an ane, so it's going to be hexane. And the prefix, well, you've got to look, haven't you? Because you need to know about this additional methyl group that's been added on here. And you need to number, so the methyl group is at the lowest, the smallest number. So if I counted this way, that'd be 1, 2, 3, 4. If I counted the other way, 1, 2, 3, we count this way. So that's carbon 1, carbon 2, carbon 3. And the methyl group is on carbon number 3, isn't it? And because you'd call it a substituent, it's not part of the main chain, it's coming off the main chain. So when you write out the structural formula, that substituent is going to be written in brackets. And because it's at position number 3, the prefix is going to be, well, 3, and it's a methyl group, isn't it? Excuse my writing. That's a methyl group. And you always have a hyphen between numbers and words. So string all that together, the prefix is 3-methyl-hexane. So the formal name is 3-methyl-hexane. And the structural formula then is just writing out what you had in the displayed formula over here. So you've got CH3, it's over there, then CH2, follow along with me. Then you've got CH, haven't you? That's the next one along. And then this substituent, this bit that's this methyl group that's coming off the chain, is not part of the chain. So you showed that's not part of the chain in a bracket there, because it's a substituent. Then continuing along the chain, you've got CH2, you've got CH2 again, you've got CH3. That's the structural formula of that isomer, and it has the name 3-methyl-hexane. All right, next one. Because you've got to get 2, haven't you? 2 structural isomers. The next one is like this. You've got that. You've got the carbon chain here. You've got another methyl group. Make sure you've got 4 bonds on the carbon. And then you've got another methyl group here. And then you've got another hydrogen atom there on the carbon. And then you've got CH2, excuse me, and then you've got CH3. Okay, same again, we've got to work out the prefix, the stem, and the suffix. Well, what's the longest chain? You've got 1, 2, 3, 4, you went that way. 1, 2, 3, 4, 5, you went that way. 1, 2, 3, 4, 5. 5 is the longest chain, so the stem there is going to be 5. The word for that is pent, isn't it? The suffix, of course, this is an alkane still, so the suffix hasn't changed. Pentane. And now you've got, well, if we're counting the chain, let's do it this way. 1, 2, 3, 4, 5. Then we want to try and have the lowest numbers. So that could be 2, 3. If we're counting the other way, that would be 3, 4. So let's have it at 2, 3. And those are both substituents, aren't they? If we're looking along the chain along there. So that's in brackets, that's in brackets. We've got 2 methyl groups, so that's dimethyl, isn't it? 2 methyl groups. And then the numbering is at number 2 and 3, and the numbers are separated by a comma, and the number and the words are separated by a hyphen. So your whole word well, the whole name there for this isomer is 2,3-dimethyl pentane. 2,3-dimethyl pentane. That's its name. And the last thing was that we just need to make sure that there were chiral centers in these molecules. So that means there's 4 different groups joined to one carbon atom. Well, if I just put an asterisk there, that's the chiral center, isn't it? Because you've got CH2, CH3 there, CH3 there, H there, and then a chain over here. And with this one, the chiral center is actually there, not there, because that carbon would have a methyl group above it and a methyl group on the left, so it doesn't have 4 different groups around it or atoms around it. This one genuinely does have 4 different groups or atoms around it. It's got a methyl group there, it's got this group on the left, it's got a hydrogen atom there underneath, and then you've got this CH2, CH3 group on the right. So it genuinely has 4 different groups around it. The chiral carbon I've just marked up with an asterisk there. So that was quite hard work, but you are getting 4 points there. And we worked out the names from the prefix, the stem, and the suffix, and we worked out the structural formula by looking at the displayed formula and then writing it in the structural formula. So I haven't done that for this one here yet, have I? So let's just work that out. So we've got a CH3, which is there, then the CH, which is there, and then because there's this substituent here, that's going as CH3, and this substituent here is going on the next carbon, isn't it? So there's another bracket there for CH3, and then you finish it off with CH2, CH3. So we've got the name 2,3-dimethyl pentane and the structural formula there with these substituent methyl groups correctly separated in their brackets to show that they're not part of the main chain. Good, we had to work hard for 4 points there, probably getting onto something a bit easier here. Complete combustion. So this is really GCSE knowledge, isn't it? Because when you take any hydrocarbon, heptane here, what was the formula? C7H16. So just get rid of that pop-up menu there. So that's C7H16. So it's complete combustion. Well, you know from GCSE that when you do complete combustion of a hydrocarbon, then you make, of course, carbon dioxide and water. And it's the combustion, so you're reacting this in excess of oxygen. So 7 carbon atoms in the reactant is going to give 7 molecules of carbon dioxide. 16 atoms of hydrogen in the reactant is going to give, well, 8 atoms of water, because each water molecule has 2 hydrogen atoms. And so if you now you've got to work out, well, how much oxygen have I got? Well, you've got 14 oxygens there, you've got 8 oxygens there, 14 and 8 is giving you, 22, but this is an oxygen molecule, O2, so if there's 22 oxygen atoms, there's 11 oxygen molecules, dioxygen molecules. That's pretty easy stuff, kind of GCSE knowledge, really. Write an equation for the incomplete combustion of heptane leading to the production of a solid pollutant. Now, when you're talking about incomplete combustion, you naturally think, don't you, of not making carbon dioxide, but making carbon monoxide. That's often what you think about with incomplete combustion. But carbon monoxide is a gas. And they're saying, well, this incomplete combustion goes to a solid pollutant. So it can't be carbon monoxide. Well, what's the other possibility? The other possibility is soot. That when you're burning this, you're burning it with a smoky flame. You're seeing particles of soot. Soot is just solid carbon. So again, you've got this alkane, haven't you? The heptane. And so you're going this occasion to making not 7 molecules of carbon dioxide or even 7 molecules of carbon monoxide, but 7 carbon atoms. This is just soot that gets burned in this incomplete combustion. Of course, you're making the hydrogens all completely being oxidized, or it's being combusted here as well. So you've now got 8 oxygen atoms, and so you're going to have 4 oxygen molecules. All right. But the point was there that instead of making any of these gases, you're looking for a solid. The only solid you can get is these carbon atoms, little particles of soot, actually. And then you've got 1 mark here for a problem that when you have incomplete combustion, you sometimes get unburnt hydrocarbons. Well, there's only 1 mark here, and really, I think where they're going here is that when you get unburnt hydrocarbons, those are being released, say, from incomplete combustion in a car engine. So we're going a little bit deeper than 1 mark here, but the incomplete hydrocarbon that comes out of the car exhaust, you can call that a primary pollutant. So I'm just working on some language here for you. Now, but when it gets in the atmosphere, it reacts with oxygen radicals in the atmosphere and forms a secondary pollutant. So that's a pollutant that is derived from the primary pollutant. So with oxygen radicals in the atmosphere, this primary pollutant goes on to form a product, the secondary pollutant, and that is called a peroxyacetyl nitrile. Peroxyacetyl nitrile. And those secondary pollutants, those reactions of oxygen radicals with a primary pollutant, the unburned hydrocarbon, is a peroxyacetyl nitrile, and those chemicals are highly toxic, and they can cause irritation or severe irritation to eyes, and there's other sort of health consequences of these sort of family of compounds, which we can just call PAN, short for peroxyacetyl nitriles. And so I think, you know, you're only getting 1 mark here. I've kind of overdone it here, but you could say that these hydrocarbons go on to react with oxygen radicals to form this class of compounds here, which are toxic, and that's an environmental consequence of having unburned hydrocarbons emitted from incomplete combustion in cars. Okay, so this is a reaction now between an alkane and chlorine, and it's talking about this reaction in the presence of UV light. Well, this is a very familiar type of reaction of alkanes with chlorine, and the type of reaction is a substitution, because you're going to be knocking off these hydrogens and replacing them with chlorine atoms. So it's a kind of substitution reaction. And later on we'll see that the mechanism for the reaction involves atoms or molecules which have an unpaired electron, and they're called radical atoms or radical molecules. So the overall name for the mechanism, which is what they want, is that it's radical because there's unpaired electrons in some of the species that are taking part in the reaction, and it's substitution because we're going to, you can see here that the hydrogen that was in the alkane has been substituted for a chlorine atom that was in the chlorine molecule. It's a substitution reaction. Okay, so now you've got to describe that mechanism in more detail. We expect to see some radicals in there. And the important point, I mean, there's a lot of marks here at stake, aren't there? 5 points. So you've got a lot of space, and you've got 3 important stages of the mechanism. You've got initiation. That's how the reaction starts. And then you've got propagation. That's how the reaction continues. And then you've got termination. That's how the reaction ends. All right. So, you know, you've got 5 marks here, and, you know, maybe 2 or 3 of those marks are looking for the stages in this mechanism: initiation, propagation, and termination. So initiation, well, you've got the chlorine molecule, you've got ultraviolet light. The ultraviolet light is going to break the bond there, and it's going to break it so that, remember, in a bond there's 2 electrons, it's a pair of electrons. It's going to break that bond in what's called homolytic fission, which means that each atom gets one of the electrons that was in that bond. So one of the electrons is going to go to that chlorine, and one of the electrons is going to that chlorine. So you're going to get two chlorine atoms, each with an unpaired electron. So those are, they're just chlorine atoms actually, but for the purposes of this mechanism, you're looking at those and seeing the unpaired electron. So that's a radical. And radicals are extremely reactive chemical species. And so they go on to react with the alkane. So you've got the alkane, which is the C7H16, and then you've got this really reactive chlorine radical, and that's going to react to give where it's, the chlorine is going to react. It's going to pull one of the hydrogens off the alkane. So the alkane has now, what's going on here? The alkane has lost a hydrogen. It was H16, it's now H15. And that's a molecule here. So the radical now is there, okay? And because this is a propagation step, we don't want to finish the reaction. We just need the reaction to continue. And the reaction continues because that radical, again, like the other radical here, is extremely reactive. So you've got that radical, and if there's another chlorine atom around, well, what's going to happen is that you're going to get now that forming. So we've finally got our substitution. We've lost a hydrogen, we've replaced it with a chlorine atom. So that's now not a radical, and a radical is, if you like, regenerated, because in this whole step here, you can see the radical was used up there, but it's been regenerated there. And so this propagation step just keeps the reaction going because the thing that got used up is produced at the end of the mechanism. It's a propagation step. The termination step, well, pretty obvious what that is. That's how the reaction ends. And reaction ends when two radicals combine to form a molecule that's not a radical. So, for example, you could have this radical that we had around from up here, didn't we? And if there's a chlorine radical, then those two can react to form the substitution product, which is that. Or it's possible, actually, to get two of these to react. That's a radical there, and another radical there. And those are going to react to form, well, if you join those together, you're going to get C14H30 as one of the possible products. So, you've got 5 marks here. It's quite a mark-heavy question. You've got your 3 steps. That's definitely worth 2 or 3 marks. And you need to be showing that you're forming radicals. And you show those in these chemical equations with a dot. That means an unpaired electron. And then you've got some equations here to show the initiation step. It's homolytic fission. The propagation step, where the radical is consumed, but it's also produced. So the reaction continues. And then the termination step means that the radicals are consumed. At the product side of this reaction here, you don't have radicals anymore, you just have molecules. Good, so 5 marks to be taken there. Right, last question in this paper. And what this question is driving at here is you've got this halogenoalkane. You've just got C3H3, CH2, Cl, and you've got a couple of reactions. And what they're really driving at here is that one of these reactions is a substitution, and one of the reactions is an elimination. Now, I suppose that might be left over because earlier on, when you were thinking up here, it was asking you about, where was it? Didn't it ask? Oh yeah, so up here, it was asking about mechanisms of reactions and asking what type of thing it was. So up there we had radical substitution. So already in our brain we started thinking about different types of reactions. So you might spot that here this is a substitution, isn't it? Because you're substituting the chlorine atom for the hydroxyl group. It's a substitution. But over here, well, actually what happens later on, we'll get to it in a moment, is you end up with ethene, and the molecule that you're eliminating is that you're eliminating hydrogen chloride. You're taking a hydrogen from one atom, and the one carbon atom, and the chlorine from the other carbon atom. You're eliminating hydrogen chloride, and you end up with ethene. So one of these is a substitution reaction, there it is. One is an elimination reaction, but you start with the same reactant, and it's just the reaction conditions that mean either the substitution is favored or the elimination is favored. All right. So, well, that's a bit of context to the equation. You'll see, sorry, that's a bit of context to the question. You'll see how that all falls out later on. But just up front, you know, you should have a few warning bells running that this looks like it's a reaction, or sorry, it's a question about substitution reactions and elimination reactions. That's just in your mind. But for equation 2, well, it's just asking, well, you know, how do you convert an alcohol to a halogenoalkane? Well, that's just something you have to know. And a good chemical for that is phosphorus pentachloride, or you might use thionyl chloride. Personally, I'd use that one. And then you've got an equation plus pentachloride. Actually, the examiner was complaining that students weren't distinguishing very clearly between the suffixes of 2s, 3s, and 5s, and I'm having the same problem this afternoon because of this computer pen. But there's a 3, there's a 2, there's a 5. The examiner is saying that students aren't always clear. I need to be clear about that. So, and that goes to the halogenoalkane, which is CH3, CH2, Cl. This is reaction 2, isn't it? We're going from an alcohol to the halogenoalkane, and the products as well is HCl and PCl3. So they're giving you 2 marks for that equation to make your halogenoalkane from your alcohol. Now for reaction 1, that's the substitution reaction. Okay. Now to get the substitution reaction, well, you need well, sodium hydroxide, or you could use potassium hydroxide, doesn't really matter which one. And you need to make sure that you've got lots of OH minus ions, because there's going to be a nucleophilic attack, nucleophilic substitution on the carbon next to the chlorine to give us reaction 1. So that reaction, the substitution reaction, you need lots of OH minus ions, and they come from sodium hydroxide or potassium hydroxide in water. So that's aqueous. Spell that right for you. And you're going to heat it. Now, the thing is, when they come to these conditions, and they talk about the reagents that you need. Well, we needed sodium or potassium hydroxide. We need it to be aqueous, because we need lots of hydroxide ions around for the substitution reaction. We need to heat it. But the other thing when they come to conditions is they're usually expecting you to distinguish, do you need to distill something or do you need to reflux something? Now, if you distill something, that means a product is removed as soon as it's formed. If you reflux something, that means the reactants stay producing product because you don't want to remove the product. And so on this occasion, there's no reason that we need to remove the product, so we can just heat it under reflux. There's no reason that we need to remove the product as it's formed. The reason you need to do that is if the product can go on to form a secondary product. The first product itself gets changed and forms something else, and that means you need to remove the product as soon as it formed. We don't need to do that here. Nothing more is going to happen to the halogen or alkane once it's formed. So you can just heat it under reflux. You don't need to remove it as soon as it's formed. Now, okay, so we had our warning bells running earlier on. That's the substitution reaction. We're now moving over to the elimination reaction. And if we draw this molecule out, this is the displayed formula. Let me help you a bit. If I draw it out like that, that's the displayed formula. What you're eliminating is hydrogen chloride there. Yes, you're eliminating HCl, and that leaves behind ethene because you've eliminated hydrogen chloride. Yeah, and you've made HCl. And the reason you get the elimination reaction is because you're not anymore in an aqueous solution. You're in ethanol, and you don't have a large amount of OH- ions. And that means you can do the elimination reaction in ethanol as a solvent, or you do the substitution reaction in water as a solvent. Now, at the end of that reaction, they're going to add silver nitrate or acidified silver nitrate. Alarm bells are ringing already. Well, acidified silver nitrate is a test, isn't it, for chloride ions, because you've got some dissociation to give you hydrogen plus and chloride minus. So you're doing the test for chloride ions, and when you add silver nitrate acidified to chloride ions, then you get a precipitate. And for your full mark, the examiner is saying you must say it is a white precipitate. And the reason you're getting the mark there is because the white precipitate you get with chloride ions. With bromide ions, you get a cream precipitate. With iodide ions, you get a yellow precipitate. So silver nitrate is used as a test for these halide ions. You get a precipitate with halide ion, but the color of the precipitate allows you to discriminate between the different types of halide ions. White for chlorine, cream for bromine, white for chloride, cream for bromide, yellow for iodide. All right, so we've got to write an ionic equation using state symbols for the reaction we set up here. Now, the ionic equation is, well, let me just put down the full equation. So you had silver nitrate plus you had hydrogen chloride, and that's going to silver chloride plus that's the full. But what the examiner is saying is you've got to look for not the full equation, but the ionic equation. So if you think about this, the ions involved there are silver ions and nitrate ions. And you've got hydrogen ions and chloride ions. And remember, this forms a precipitate. So that's a solid. Sometimes you can draw an arrow going down to show that it's a precipitate. But this is still in solution. Remember, everything's in solution here. You've got a hydrogen ion in solution and a nitrate ion in solution. And the examiner is saying, well, hang on. You've got a hydrogen ion in solution and a nitrate ion in solution. You've got a nitrate ion in solution. You've got a hydrogen ion in solution. Nothing's changed. Here you had a hydrogen ion and a nitrogen ion in solution. Here you had a nitrogen ion and a hydrogen ion in solutions. Nothing's changed. And so what you can do is you can remove the ions when nothing changes. And they are called spectator ions. You can think of them as not being involved in the action, not being involved in the reaction. They are just spectator ions. They're not doing anything. So the examiner is saying in an ionic equation, you don't include the spectator ions. So that was, I mean, negative there, don't I? How do I do it? I made a mistake there as well, didn't I? That's because I'm talking and writing at the same time. Sometimes it doesn't work. So these are the spectator ions. So we're going to now say, well, the spectator ions are the same in this side of the equation and in this side of the equation. So that spectator ion isn't doing anything. 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 We can, for the purposes of this equation, we can ignore them. So the ionic equation removes the spectator ion and just focuses on the ions that are involved in making the precipitate. And you've got silver ions that are aqueous, chloride ions that are aqueous, and they make the silver chloride precipitate, which is a solid. Now you're only getting 1 mark for that, but you've got to get these ions without the spectator ions. You've got to get these state symbols. You've got 2 that are in solution, and the product is a solid. And for all of that, you're getting 1 mark. And in the examiner's report, the examiner said a lot of students weren't familiar with what an ionic equation is. It's an equation where you have only the ions that are forming the precipitate, and you leave out the spectator ions. Good. Now, you've got the last point over here. You've got this alcohol, ethanol. You've got an oxidizing agent. And you know that when you oxidize an alcohol, first of all, you form, you form an aldehyde. Okay. Now, if you keep heating it with an oxidizing agent, the aldehyde is further oxidized. And if you further oxidize an aldehyde, it becomes a carboxylic acid. So you had ethanol, you oxidize it first of all, it becomes ethanal. If you keep oxidizing it, it becomes ethanoic acid. But they've got this distillation happening here. And if you remember, you said, or we said, that you distill something when you want to remove the product as soon as it's formed. And that's the case here, isn't it? We want to remove the ethanal as soon as it's formed, because if we leave it in the mixture with potassium dichromate, it's going to be further oxidized to ethanoic acid. So what's the ionic product that's distilled out? Well, it's the first thing that gets oxidized. It is ethanal, an aldehyde. It is distilled out of the reaction mixture as soon as it formed. Then finally you have to explain why this distillation worked. You see, what happened is you had alcohol, and it was forming, sorry, that's ethanal, isn't it? Sorry, ethanol, the alcohol, and it's forming ethanal. And this is boiling off as soon as it's formed. It's distilling. And that only works, doesn't it? Because the boiling point of ethanol, boiling point of ethanol. So in terms of boiling points, ethanol has a greater boiling point than ethanal, and that's why we can do the distillation. And we've got to explain in terms of intermolecular forces and properties, because explain in terms of the properties and the intermolecular forces why ethanol has a higher boiling point than ethanal. Well, the boiling points are influenced by two things. One is the relative molecular mass, and one is intermolecular forces. Now, the relative molecular mass for ethanol is 24 plus 16 is 40, is 46, isn't it? And the relative molecular mass for ethanal is 24, 40, 44. So it's true that the relative molecular mass of ethanol is more than ethanal, and so that will give it a slightly higher boiling point. It's just a little bit more massive, but it doesn't feel like a particularly strong argument because the difference between these relative molecular masses is quite small. But when you come to intermolecular forces, then the alcohol has hydrogen bonding, excuse my writing, the alcohol has hydrogen bonding, but ethanal only has dipole intermolecular forces. I mean, they both have dispersion forces as well, but the hydrogen bonding is a stronger intermolecular force than dipole-dipole interactions. And for that reason, alcohol has a higher boiling point than ethanal. And that means that because ethanal has a lower boiling point than ethanol, then it can be boiled off as soon as it's formed in the distillation. Good. Well, that's the end of this paper here. To sort of recap some of the examiner's points, the ionic equation was an area where the examiner felt that the students were weak. Not saying a white precipitate, the examiner felt that the students were weak. This was all done quite well. You had to distinguish between substitution and elimination reactions. The examiner was finding actually that students were quite good with initiation, quite good with termination, but they were a bit fuzzy about writing propagation reactions. So make sure you know that, because the examiner says that students are generally weak at propagation mechanisms. All this was done quite well. Naming is good, writing out the structural formulae, that's quite good. Definitions you just have to learn. When you're writing your descriptions here, use some bullet points. Make sure you're getting your 3 points there with your 3 or 4 bullet points. This was all quite well done. All done quite well. If you remember, some students here were mixing up their ratio of aluminium to chlorine, so it's AlCl3. We had a long discussion there, didn't we, about ceramic materials? And that's right, the examiner is making sure that when you specify a conductor, you're specifying an electrical conductor or a thermal conductor, and that's true for insulators as well. And points were being deducted for not specifying or being specific about the kind of conductor that was being used. All right, so that's AS level structured chemistry paper from Cambridge International Examinations. So if there's other questions you've got about that, then the Z coaches are on the Slack channel, and you can speak to them there about any questions that you've got that remain from going through that paper. So it'd be great if you wanted to post questions on the Slack channel for the Z coaches. It'd be great to get to know you there. But otherwise, I wish you every success with your studies in chemistry, and look forward to you joining our next masterclass, where we go through papers from Cambridge International Examinations.